Hello and welcome to this session. LO4, understand the fundamentals of logic circuits and gates. In this session, we will explore a key question. How do computers perform complex calculations using only zeros and ones? This video introduces the fundamentals of logic circuits and gates, which form the backbone of all digital systems. You'll discover how these components enable everything from simple decision-making to sophisticated arithmetic operations, powering the devices and applications we use every day. Binary, decimal, and hexadecimal are key number systems in computing. Binary uses zeros and ones to represent data, aligning with electronic circuit states. Decimal is familiar in everyday use, while hexadecimal simplifies binary by grouping bits. Each system has unique advantages. Understanding these systems is crucial for data representation in computers. Logic forms the basis of decision-making in computers. Propositional logic deals with truth and falsehood, using operations like and, or, and not. These operations manipulate binary values to produce desired outcomes. Understanding these basics is foundational for more complex logic. Explore how these operations form the core of computing processes. Logic gates are the building blocks of digital circuits. They implement Boolean functions with binary inputs and outputs. Common gates include and, or, and not, each with specific functions. NAND, NOR, XOR, and XNOR expand these operations. These gates form the basis of all digital logic circuits. Logic circuits are categorized as combinational or sequential. Combinational circuits' output depends only on current inputs. Examples include adders and multiplexers. Sequential circuits consider past inputs, incorporating memory elements like flip-flops. Understanding these distinctions is key to grasping circuit functionality. Truth tables display all input-output combinations for logic gates. Boolean algebra simplifies logic expressions, optimizing circuit design. Key laws include identity, null, and involution. De Morgan's theorems provide transformation rules. Mastering these concepts aids in efficient circuit implementation. Logic circuits power many real-world applications. Calculators use them for binary arithmetic. Traffic systems rely on sequential logic for state changes. Alarms use combinational logic for condition checks. CPU registers store and process binary data. These examples highlight logic circuits' versatility. Binary is the fundamental language of computers. It uses zeros and ones to encode all data types. Binary fits electronic circuits' on-off states naturally. This simplicity enhances design reliability. Understanding binary is crucial for grasping computer operations. Different data types are represented in binary. Unsigned binary represents non-negative integers. Signed binary, using 2's complement, handles negatives. Text uses ASCII or Unicode for character encoding. Images and sound are digitized into binary forms. Each type has specific encoding methods. Conversion between number systems is essential. Decimal to binary involves dividing by 2 and recording remainders. The reverse involves multiplying by 2. Hexadecimal simplifies binary by grouping bits. Mastering these conversions aids in understanding computer data processes. Logic operations manipulate binary values, and outputs 1 if both inputs are 1, or outputs 1 if at least one input is 1, not inverts the input value. Understanding these operations is key to designing logic circuits. Beyond basic gates, advanced ones like NAND and NOR exist. NAND outputs 0 only if both inputs are 1. NOR outputs 1 only if both inputs are 0. XOR outputs 1 if inputs differ. XNOR outputs 1 if inputs are the same. Transistors implement logic operations in circuits. They act as electronic switches to form gates. MOSFETs are common in digital logic. NMOS conducts when voltage is applied, PMOS when none is applied. Understanding transistors is crucial for circuit design. Transistors form the basis of logic gates. A NOT gate uses one NMOS and one PMOS transistor. AND gates use NMOS in series and PMOS in parallel. OR gates use NMOS in parallel and PMOS in series. AND and NOR are universal gates, forming any operation. Complex arithmetic operations build from basic logic. Adders use XOR and AND gates for binary addition. Multipliers use repeated addition and bit shifting. Dividers use subtraction and comparison. Understanding these builds insight into digital computation. Addition is fundamental in digital circuits. Half adders use XOR for sum and AND for carry. Full adders handle 3 inputs, cascading for multi-bit addition. These form the base of arithmetic logic units. Understanding adders is crucial for arithmetic operations. Subtraction uses binary complement concepts. Half subtractors use XOR for difference and no T-AND for borrow. Full subtractors handle 3 inputs, cascading for multi-bit subtraction. These operations are vital for arithmetic calculations. Mastering subtraction is key to digital logic. Binary multiplication involves repeated addition, and gates generate partial products. Adders sum these products, often using array multipliers. Larger multiplications use algorithms like Booth's. Understanding multiplication is crucial for complex arithmetic. Binary division is complex, using sequential logic. Comparators and subtractors handle division steps. Shift registers manage data flow. Control logic orchestrates the process. Understanding division is key for complex digital operations. Arithmetic logic uses combinations of gates. Addition uses XOR and AND gates. Subtraction involves XOR and not and or. Multiplication relies on and adders. Division requires more complex arrangements, often using sequential logic. In conclusion, mastering these skills unlocks the full potential of digital computation. We appreciate your attention. Should you have any questions, please contact UKversity via WhatsApp at 07484 361,688. Thank you, and we look forward to seeing you in the next session.